Hi, welcome to the lecture series on image recognition with neural networks. This is lecture 2, functions and their computational graphs. So the objective for this lecture is we're going to talk about multivariable functions. We'll talk about real value versus vector value functions. We'll talk about parameters of a function, computational graphs, and neural networks. And then we'll have a brief introduction to Numpy, which is a library that allows us to do optimized linear algebra, basically matrices and operation, matrix multiplication, matrix addition, and broadcasting. Okay, let's get started. Just to standardize the notation, we'll just denote R for all the real numbers, and then for the n-dimensional Euclidean space, Rn, that will be the set of all vectors of this form, where there's n entries, each of which is a real number. And to save space, sometimes we will denote this vector horizontally by transposing it. So T here is for transpose of a vector. So R squared is the familiar two-dimensional space, the xy plane. R3 is the three-dimensional space. A function f from a to b is a rule that assigns to each x in a unique f of x in b. So the set A is called the domain of f, and the set B is the codomain of f. So in algebra, usually we have A and B as the real numbers. So for example, f of x is x squared. It's a function from the real numbers to the real numbers. This is the graph of a parabola. We saw this logistic function in the first lecture. So here's the graph of it. It's 1 over 1 plus e to the negative x. It has domain all real numbers, and the output is from 0, 1. But in general, a function can have higher dimension domain and codomains. So for example, in precalculus, you might remember parametric functions, which is a function from the real numbers to R squared. So as an example, here's a parametric function. It takes t, which is the input, and then it returns a two-dimensional vector, t squared. So for example, if we were to graph this, and t is going to go from -1 to infinity. So when t is -1, you get the point -1, 1. When t is 0, you get the point 0, 0. As you keep going, as t increases, then we have this graph that increases like this. You might have seen this in precalculus, but you might see it in this form, where it's given that x of t is t and y of t is t squared. So again, this is a parametric function. So in multivariable calculus, we study surfaces, which are basically graphs of function where the input is R squared and the output is the real numbers. So for example, here's a f of xy. The input is xy, which is a vector in R2, and the output is a number 3x plus 4y plus 2. This is a graph of a two-dimensional plane in three-dimensional space. So here's what it looks like. So again, the input is xy. So the input is actually all the points on the floor. So this is the xy plane on the floor, and then the output is a real number. So that's the height of so that all these points right here on the plane is the height given by 3x plus 4y plus 2. Here's another example. F of xy is x squared plus y squared. This is the analog of a parabola in 3 space, and so it looks like this. So once again, the xy plane is the input, and then for every xy input, the output is the z coordinate, which is the height of the function. In general, we want to make the distinction between real value function and vector value function. So real value function is a function where the output is a real number. So it doesn't really matter what the input is. As long as the output is a real number, then this is a real value function. So for example, we saw this function earlier. Again, it doesn't matter that this is R squared, because the output is a real number, and this is a real value function. Similarly for this one, this is also a real value function. A vector value function is a function where the output are vectors, where the dimension is bigger than 1. So again, it doesn't matter what the input is, as long as the output are vectors whose dimension is bigger than 1, then that is a vector value function. So for example, here's a kind of the formal form of this. So the input is a vector of Rn, but again the output is what matter. This output is a vector of dimension m. So this f1 is the first component of that output, f2 is the second component. So notice these component functions are actually view value function, because this function right here output one number, and that number will be the first entry. So this is what a vector value function looks like. This is basically joining together a bunch of view value functions. So for example, this is a vector value function because again, the output is a vector. So this is f1 and this is f2. It will be two component function of f. This is also a vector value function. There's three components, f1, f2, f3. And we learned from precalculus and in algebra that given two functions, we can create new functions by defining various operations on them. For example, we can add functions, subtract, multiply, and divide functions. Another important operation is function composition. So this is true in precalculus as it is in multivariable calculus. If I have two functions, f from Rn to Rm, g from Rm to Rk, then we can compose them. Notice for us to be able to compose this, notice the output of Rm has to be the input of the output of g has to be the input of, the output of f has to be the input of g for us to be able to compose these. So g circle f is the composition of g and f. In fact, the order of operation here is that we're going to apply, given an input x, we're going to apply f first and get the output of f. And then we take the output of f and input it into the function g. So again, we apply f first and then we apply g to it. So for example, here are two functions. G circle f is applying first f of x is x squared in this case, and g of x is 2x plus 1, so g of x squared is 2x squared plus 1. So the output of f becomes the input of g. In the same way, we have a vector value function. It's the same thing. So for example, g circle f, again, the input here is rq, because that's the input of f. So we apply f first. So f applied to this vector will give us this vector. So we have that. And then g will take the output of f and then input it into g, which take the sum of the entries. So we take the entries and sum them. And so this is the output of g circle f. Parameters of a function. So we saw this in the first lecture where we saw a linear function f of x is mx plus b. We talked about how x is the input of the function, but m and b are parameters of f, so that we can, as we modify m and b, we modify our linear function. So as an example, you might have done linear regression in precalculus or in algebra, and so the idea is that we have some kind of data, maybe a scatter plot, and we want to find the line of best fit. And the way it works is that there are many parameters m and b that do not describe this data, and the goal of linear regression is to find the best possible parameter m and b that describe the data. And it turns out that linear regression is a very simple machine learning algorithm. So these parameters m and b can learn from the data. The parameters are also called learnable parameters or learnable weights because they can learn from data. And so, as we mentioned in lecture 1, we denote the dependency of f on these parameters by writing the parameters after the input. So, and we separate it using a semicolon. So for example here, f of x, semicolon mb, x is the input, m and b are the parameters. Let's talk about matrices. An m by n matrix, A, again this is the notation for m by n matrix, has this form. There are m rows and there are n columns. So as an example, this is a 2 by 3 matrix, 2 rows and 3 columns. Turns out that an m by n matrix defines a function going from Rn to Rm, and this is defined by using matrix multiplication. So again, here's a function, the input is x, and a is the parameter. So if I change the parameter a, then I've changed my function. This is a linear transformation. So for example, if a is a 2 by 3 matrix like this, then that means it defines a function going from R3 to R2. So given a vector in R3, the definition of this function is we multiply it by matrix A. So here's A, and here's the input x1, x2, x3, which is a vector in R3. When we matrix multiply, as a quick review, x1 times 1 plus x2 times 3 plus x3 times 2. We add them together, and so we write that as first entry. We take this whole column and do this again for the second row and get the second entry. So again, please review. Matrix multiplication is a very useful and very important part of machine learning. We'll do some more example when we do Numpy later today. Now, if we have an m by n matrix A and a column B, which is m by 1, then this defines an affine function from Rn to Rm, just like before, given by, we take the input x, again these are parameters, A and B, you multiply x by A, and then you add the vector B to it. So again, this is called an affine function. So for example, here's a matrix and here's a column vector. Together they define a function from R2 to R2, where you take the input, you multiply by A, then you add the column B. And when we add it together, we get this function. So this is a vector value function from R2 to R2. It's useful sometimes in machine learning to be able to have a function defined on matrices. And so a function defines on an m by n matrix that is a real value function, so that the output is a real value. So for example, here's a function that is defined on a 2 by 2 matrix, and it outputs a real number because it's a real value function. And all it does is that it squares all the entries and then add them together. So we'll see this a lot when we start doing the neural networks. So this function ax plus b is an affine function. So technically, we can use this to be able to learn from our data and be able to make prediction. In fact, it turns out that if we use ax plus b, where a is a matrix and b is a column vector, then this is called linear regression. And in fact, in the linear regression case of algebra or precalculus, a is simply one number, which is the m, the slope, and b is also one number, which is the y-intercept. So this is a way to generalize linear regression in precalculus, where it's only one variable. But now we have multiple variables. For example, if we were to predict the value of a house based on many parameters, like many different variables, such as the number of bedrooms, the square footage, etc. All those features of a house would be the vector x, and then finding the best A and best B would help us compute the price of a house. So all that is part of linear regression. Unfortunately, this is a linear function, so we can't use it to do anything more complicated. For example, recognizing images, we can't just use a linear function because it's too simple to be able to extract the complicated information from images. So we like to have a non-linear component. We mentioned in the first lecture that if we have a function that takes real numbers and output a real number, we can extend that into a vector value function from Rn to Rn by applying f component-wise or element-wise. So given a function, a real value function, we can extend it to a vector value function by applying f individually to each of the entries of the vector x. We can do the same thing if the input is a matrix. Again, we just apply it component-wise if the input is a matrix. So for example, we saw that the sigmoid function, we can extend it. So if we're supposed to have a matrix, 2 by 2 matrix, then we can extend sigma into a function from R22 to R22. Again, this is the 2 by 2 matrix. And the way we do it, we're just going to do it component-wise. So sigma of A is sigma of 0, sigma of 1, sigma of -1, sigma of -2, and that's the output. It takes a matrix and output a matrix of the same dimension. Sigmoid won't change the dimension. So amazingly, we mentioned in the first lecture that these two functions, the affine function and the sigmoid function, with the appropriate parameters, can be combined in a way that can give us a score function that can recognize images. So now we want to explore Numpy so that we can kind of know how to use some of these operations, be able to do some basic matrix multiplication, etc. And so let's do that. We're going to jump to the Jupyter Notebook. Okay, so Numpy is basically a core library for scientific computing, allows to do optimized operation in linear algebra like matrix multiplication, etc. So we first import it. So import NumPy as NP. So NP will be now the name of NumPy. It's just a shorthand notation, standard way to input the library. So again, we're going to deal with mostly just arrays, multi-dimensional arrays. So an array is simply just a grade of values. So let's start with the one-dimensional array. So I'm going to say np.array, and then in parentheses, I'll just put one-dimensional array, 1, 2, 3, 4, say. Let's print out the shape of this matrix, and then print out A itself. So if I do that, notice the shape is 4, with a comma, nothing after that. So this means that this is one-dimensional. It has a length 4 in that dimension, and you print it out, and it's 1, 2, 3, 4. Now in this class, we're going to deal exclusively with only 2D arrays, so let's focus on that. So to create a 2D array, we're going to say np again, array, and this time we need to have a two-dimensional array. So here's the outer brackets, and then in the inner brackets, I can say here's the first row, 1, 2, 3, and then that's the first row of this 2D matrix. Put a comma here. Here's the second row, 4, 5, 6. So this is a two-dimensional matrix that has 2 rows and 3 columns. So let's print out B and the shape. So B, there it is, 2 rows, 3 columns, and the shape is 2, 3. So again, 2 rows, 3 columns. We can also randomize these matrices. Instead of creating values manually, we can randomize it. So for example, we can say np.random.rann and 2, 3. So we want 2 rows and 3 columns. This is going to randomize our values, and the value is going to come from the standard normal distribution, which is the distribution with mean 0 and standard deviation 1, and it looks like the bell curve. So let's do that. So notice here it generates a 2 by 3 matrix, of which comes from this distribution. Okay, let's do some basic review of matrices and some of the operations. So here's again m by n matrix we saw in the lecture, and the shape of this is m comma n as we saw in NumPy. So we denote A to be Aij, B is Bij. So let's talk about how to add 2 matrices and how to subtract 2 matrices. And from precalculus, we learned that adding and subtracting is done component-wise or element-wise. So for example, given these 2 matrices, they need to have the same dimension. When we add them component-wise. 1 plus 5, 2 plus 6, 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, 4 plus 8 is 12. So here is I create here the matrices, these matrices. So 1, 2, 3, 4, 5, 6, 7, 8. And to add element-wise, like this, it's very simple. In NumPy, you just say x plus y. There it is. There's 6, 8, 10, 12. And again, this is element-wise addition. This is element-wise difference, x minus y. You just write x minus y. And even though these are matrices, we just follow the element-wise operation that we just defined. So there's element-wise difference. This is now scalar product. So a scalar product is basically we take a matrix and you multiply it by a scalar. And what that means is that by definition, we take that scalar and we multiply by every entry of the matrix. So 3 times 1, 3 times 2, 3 times 3, 3 times 4. So we get that matrix on the right. So let's do this in code. So we just say 3 times, and then let's just do it for the x matrix we saw earlier. So there it is. This is 3 times the matrix x. Again, x is this matrix earlier, 1, 2, 3, 4. So that's scalar product. We just stretch out the matrix or vector by a factor of 3. There's also another, the element-wise product is also defined. So given 2 matrices of the same dimension, This is called the Hadamard product, which is simply element-wise product. So A times B is simply the corresponding energy Aij times Bij. So for example, here two matrices have the same dimension. When you multiply them, we multiply them component-wise or element-wise. So 1 times 5 is 5, 2 times 6 is 12, etc. So to do this in Numpy is very simple. You just say x times y. And that's it. So that's element-wise product. But if you remember from precalculus, you learned a very complicated multiplication called matrix multiplication. So again, that's not done by this. This is not the same thing. And so we use a function called dot from the Numpy library. And again, knowing and understanding matrix multiplication is very important in machine learning. So we'll do a couple examples, but please review it if you don't understand these examples. So for example, here's a 2 by 2 multiplied by a 2 by 1 matrix. And again, the way we do this is that we take 1, we multiply by 1, 2 multiply by 2, and then add them. So 1 plus 4 is 5. And do this again. 1 times 3 plus 4 times 2 is 11. So if I have x and v as defined like this, so again, x is 1, 2, 3, 4, v is 1, 2, just like this example. To do matrix multiplication, I say, let's print this out. So we say np dot, and we use the function called dot to do matrix multiplication, and we say this is x comma v because we want to multiply x by v. So there it is, 511. Okay, let's do another example. You might remember that there's some dimension analysis here that we need to be careful with. And so this is a 2 by 3 matrix. This is a 3 by 2 matrix. Notice for us to be able to multiply matrices, you might remember that we need the number of columns of the first matrix to match up with the number of rows in the second matrix. Because if not, then we can't correspondingly multiply as we did earlier. Right? Because if this is 3 elements and this is also 3 elements, then we can just match them up and then add them together after we multiply. So again, you can try this out and you get this. So the way we do this in Numpy is to say, again, we're going to just use the np dot, and then in the argument, we just say x comma y to multiply the matrices. And there it is, 9, 1, 4, 5, which match up with this. Now, these two matrices cannot be multiplied because this is 2 by 2 and this is 1 by 2. Again, because this, let's try it out. If I were to do this, then it'll give me an error. There it is. It's because the dimensions do not align. Let's talk about the transpose of a matrix. If I have a vector or a matrix, we can transpose it. So for example, we can say print, let's print out, so for example, let's say print out v first. Take these comments out. So this is v, and this has 1 row and 3 columns. So the shape here is 1, 3, and then I want to print out v dot t. So this is the transpose of a matrix. You say dot t, and if I do that, I notice you just flip it, and so now the shape is 3 by 1. So the rows become the columns, and the columns become the rows. So that's the transpose of a matrix. And there's a few useful functions that we'll use later in the course to do computations on arrays. So the most useful is sum. So suppose I have an array like this. I can print it out, and there it is. I'm going to sum up all the elements of this matrix. So it's very simple. You just do np.sum and just put in the matrix. And it will add up all the numbers in the matrix. So that's 21. Now, sometimes you might want to add some sum up elements, but we might not want to sum up all the elements. We might want to sum up only among all the rows or all the columns. So this is a little bit confusing, but we'll just try to be very careful here. So suppose I want to, let me just do it by example. I'll just say, so I'm going to sum up all the, I want to sum up x, but I'm going to do it along a certain axis. So let's say that I want to sum up x, but only along axis 0. Again, axis 0 is the rows. So if I were to sum up along the rows, that means all the rows are collapsed, and we are summing the columns. So let me kind of show you this here. So here's x, here 2 rows. If I were to sum along the rows, that means that these rows are going to collapse together, and I'm going to sum up. So 1 plus 4, because they're going to collapse together, that's 5. And then 2 plus 5 is 7. And 3 plus 6 is 9. So again, summing along axis 0 is collapsing the rows. So we are summing along the columns. So if I were to do that, I get 5, 7, 9. So basically look at that example. This is very important. Again, we'll use this a little bit later. Now, if I were to sum along another axis, so say I want to sum, but this time I want to add up x again, but now my axis is going to be 1. So this is summing along the columns of the array. So again, axis 1 is the columns. So now I'm summing up, I'm collapsing all the columns. So here are the columns. We're going to collapse it. So that means we're going to sum along the rows. So again, all these columns are collapsed. So I'm going to sum 1, 2, 3. That's, well, let's just print it out first. So 1, 2, 3 is 6. 4, 5, 6 is 15. So that's along the second axis, which is axis 1. And another one that we saw in lecture 1 is the argmax. So argmax will return the index of the largest value. So for example, if I want to np.argmax x, then it will return the index of the biggest value. The biggest value is 8. The index is 3, so this print up 3. Again, this is a very brief and simple NumPy introduction. So you can look at the documentation if you like. So again, this whole notebook is available under the description of the video. And one last thing we need before we move on is broadcasting. Again, this is very minimal treatment of this. This is we're going to only talk about exactly what we need for the course. Broadcasting can be very complicated in a higher dimension. So here's what we need to know about broadcasting. So for example, if I want to add up two matrices like this, notice in this case we can't add them up because they're not compatible. The dimensions don't match up. So broadcasting will take the second matrix and will basically broadcast its value so that the dimension do match up, and then we can add it. And we'll see why later this is important. This is going to be a very natural way to add matrices. So for example, we can't add these, and so NumPy will automatically take this matrix and it's going to broadcast it by making copies along the rows. That way now we have 2 by 2, and now we can add it the usual way. In the same way, again, this is now not compatible, so if I want to add this, then this needs to be broadcast horizontally so that we can now have a matrix of the same dimension as this, and again we can add in the same way as before. So again, we broadcast by making the smaller matrix compatible with the bigger matrix so that we can do the element-wise operation. Because once they have the same matrix, same dimension, we can do everything element-wise. And so that's kind of the point of broadcasting. So as an example, well these examples right here will give you these values. So let's try it out. So here's A. A is this matrix, and B is this 2D but only one row matrix. So this again, everything is two-dimensional. Even though it looks like this is one-dimensional, we'll treat everything as two-dimensional. So if I were to say A plus B, again, the nice thing about broadcasting is that this is done automatically. You don't have to worry about explicitly telling NumPy to do this. And so let me do that, and we get exactly this matrix. Is what we saw over here. And then same thing here, if I were to do A plus B in this case, this is the case where this is a column that's being broadcasted. And again, we get the same result as this. Okay, that's just all we need for the course as far as NumPy. So let's get back to the lecture. Computational graphs. So a computational graph is basically a way to represent graphically a function. It's nice to kind of have a visual representation of a function. A computational graph has two things. It has nodes and it has directed edges. So the nodes are variables or operations, and the edges are diagrams how those variables feed forward their values into the operations and how those operation output feed forward into other operations. So the edges tells you how the function flow forward. So as the best way to kind of see an example here. So here's a function wxy. It takes two variable and it's going to multiply it. So again, then the nodes here are the variables. or it could be operation. So this node is an operation, x times y, and the directed edges tells you the way the data flows. So x will go forward, y will go forward, feed forward into this node. Here's a little more complicated example. F of xy is xy plus z. So the way we draw a computational graph is we introduce intermediate variables based on the order of operation, and then we just slowly build them up to be the complete graph. So for example, if I were to give you three inputs, then this operation says that we first multiply x times y, because that's the order of operation. So when we create the graph, we take x, y, and we feed forward into the new operation x times y, and we'll give this a new name, w. Again, when we introduce these intermediate variables, we give it names along the way. Once we multiply x, y, then we can use that output to feed forward into the next part of the graph. So for example, the next part of this is you take x times y and we add it to z. So this will feed forward, and z also will feed forward to get u, which is z plus w. So the output of xy is now added to the z input. So if I were to have constants or actual data for these variables, it would just feed forward the obvious way. 3 times 2 is 6. 6 minus 1 is 5. Okay, let's draw a computational graph for some of the functions we talked about earlier. So for example, ax plus b, the affine function. So the input is x, right? This is the variable node. And then notice it feeds forward. And also, we also have parameters a and b, and those also will feed forward. Together, those three will give you a new variable, z, which is ax plus b. So that's the z operation. It's actually two operations, ax plus b. And so, again, we always want to introduce variable as we generate these nodes. Here's a more complicated example. What if I have an affine function composed with a sigmoid function? Well, the same way. Again, here's an x input. The parameters w and b, all of them feed forward to give you z, which is wx plus b. And then the output of that is feed forward into into this node by applying sigmoid. So again, we're going to use the standard notation of z is the result of an affine function, and a is the result of applying sigmoid. And that's the final output. So this is the computational graph for this composition of an affine and a sigmoid. Turns out that this picture right here, this computational graph, is a one-layer neural network. And so first, a one-layer neural network is simply applying an affine function followed by a sigmoid function. So we've seen this in lecture 1, so you can imagine a two-layer neural network is basically doing this twice. So you take x, the input, and we feed forward with the parameters w1 and b1 into z1, so that's the affine function. Then we take the output of z1 and we apply sigmoid to that. We call that a1. And then we repeat this process. We take a1 and we're going to feed forward and apply it with w2 and b2 by multiplying by w2 plus b2. We call that z2. Notice the subscript here. And then we feed that forward into sigmoid again. And we call that a2, where a2 is sigmoid of z2. So a two-layer network is basically applying what we did earlier twice, an affine function and a sigmoid 2 times. You can imagine an n-layer neural network is basically you have n affine function, and we're going to apply the combination of an affine followed by a sigmoid n times. So here's x, you feed forward into z1, this is the affine function, you feed forward that into a1, you feed forward that into z2, a2, z3, a3, all the way to zn, which is the last affine function, and then sigmoid of that is an, which is the output. And these middle layers are called the hidden layers of the network. So this picture is, I kind of drew this picture this way because that way you can see all the parameters and how everything flows. But in literature, you probably will see this picture, say on Google Images or something. And this is the same picture. So for example, for us, this is x, which is the input, just like we have over here. And then the reason why there's so many arrows because of matrix multiplication. When you matrix multiply, all these connections are formed by doing that complicated matrix multiplication. And these are hidden layers in the middle, and then the output is over here. And so again, I won't go into detail how that works, but do an example out, make sure you understand that this is really is matrix multiplication here. Okay, let's do an example. Let's make sure we really know all the something concrete. Suppose I have an image which is an MNIST image, again 784 pixel values, and we want to use a one-layer neural network, and we want the output to be a one-hot encoding of digits from 0 to 9. So what are the different dimensions of the W, B, and the output? Well, the input X has dimension, 784 by 1, and then the output has dimension 10 by 1. So for that to happen, we need W to be 10 by 784. If this is 10 by 784, multiplying that by X, which is 784 by 1, that will give us a 10-dimensional vector. And for us to be able to add that to B, B has to be compatible with that. B has to have the same dimension. So B will have dimension 10 by 1. And then finally, the output will also have dimension 10 by 1. By the way, notice that the sigmoid function does not change the dimension. So Z also have dimension 10 by 1. When I apply sigmoid to Z, A also have the same dimension as Z. Right? Sigmoid does not change the dimension of the input. So in this example, we have a lot of parameters. Notice. In fact, let's just kind of try to compute that. How many learnable parameters do we have in this network? Well, W has 10 rows and 784 columns, so that's 10 times 784. And B is 10 by 1, so together we have 7,850 different parameters for this one-layer neural network. So that's a lot of parameters. Right? And so one of the questions we want to address is that how do you know how many layers to use in the network? So that's actually something you have to be chosen before the training process. That's not part of the training data. The training process doesn't learn the number of layers because this is a parameter that does not learn from data, and it's really not part of the computational graph of the network, of the neural network that we drew earlier. So this is called a hyperparameter. Again, this is a basic course, so we won't discuss how to tune or find these hyperparameters. Instead, we're going to use a two-layer neural network. In fact, we talked about it in the first lecture that the two-layer network, we use a 30-dimensional hidden layer. Again, that's also a hyperparameter, but we're going to just use this algorithm and learn the math behind why this network actually works the way that it does to classify images. So we focus on the algorithm rather than some of the specifics of hyperparameter tuning. So we saw earlier that we have these compositions of affine and sigmoid composition. So, by the way, this is the architecture that we'll be using. Notice in this architecture we have a lot of parameters. We have W1, which is a very big matrix. B1 is a big vector. W2 is another matrix that's very big. B2 is another vector. If we multiply everything together and calculate the number of parameters, the number of entries in those matrices, then you have 30 times 784, which is the W matrix. We add to that the number of entries in B1, so 30 times 784 plus 30 plus 10 times 30 plus 10. So you have about 24,000 parameters. So it seems like it's almost cheating that we have that many parameters to tweak and modify to make this function fit the data. So there's some issue here that we're not going to be talking about. For example, overfitting. Again, maybe something for a future course. But right now, we have a lot of parameters in this network. So in the next lecture, we're going to discuss, we're going to formalize, now that we have the math language, we're going to be able to formalize the image recognition problem by introducing an objective or cost function. So this is the second lecture. By the way, I forgot to mention the first lecture that every lecture has a notebook, Jupyter notebook that has very basic programming question. Everything can be done with a couple lines of code. So we'll make sure that you familiarize yourself with Numpy and all the basic operation. And plus, some of these notebooks will ask you to write very basic function that will be used later in the last lecture, which is lecture 6, where we actually write the entire program. So please try to work on those notebooks. Okay, I hope to see you in the next lecture.